we mentioned it, cosmology, astronomy, all of that. The uncertain universe, the acceptance of the quantized nature of energy and light was only the start of the revolution that founded modern quantum mechanics. So if you think that calling light a particle, even though until that point, by E&M, by Maxwell, light was considered a wave, so we literally got the entire theory of light as a wave from Maxwell and whatnot, and then to call it a particle kind of gives rise to this initial quantum mechanics where light is a particle. Now, if you thought that that was strange, well, there was much more stranger things to come in the 20th century. Okay, for example, the uncertainty principle, which a lot of even the quantum mechanics contributors didn't even like. And so, for example, Schrödinger, who is very well known and very well regarded, very well reputed in quantum mechanics as a contributor of quantum mechanics, also actually did not really like that he had contributed to something that ended up having uncertainty and probabilistic nature. So it was not until the 1920s and the work of Schrödinger and Heisenberg that the dual nature of light as both particle and wave was finally elucidated. For a while, the existence of photons had become accepted in the previous years. There had been no way to reconcile this with the well-known wave behavior of light. What emerged in the 1920s was a theory of quantum physics built upon wave mechanics. In Schrödinger's version of systems is described in terms of a wave function, usually called psi, and psi is psi, psi, which evolves according to an equation called the Schrödinger equation. So Schrödinger actually wrote down the wave equation for matter, for a particle. And then someone else, turns out, told us later on, so when he wrote down the wave equation for a particle, he didn't realize that he was going to give us a probabilistic answer for the position as a function of time for a particle, but turns out it was going, he didn't know it, but it was going to be. So anyway, which evolves according to an equation called the Schrödinger equation. The wave function psi depends on both space and time. Schrödinger's equation describes waves that fluctuate in both space and time. So how does the particle behavior come in? The answer is that the quantum wave function does not describe something like an electromagnetic wave, which one thinks of as a physical thing existing at a point in space and fluctuating in time. The quantum wave function describes a probability wave. So this is what I mean. When Schrödinger first wrote down the wave equation for matter, he thought he was writing down the wave equation for matter, and it's sort of like this, like what are they even trying to do in quantum mechanics, right? Like quantum mechanics itself has the clue. Mechanics generally means something as simple as writing down the position of something as a function of time, for example, or even a function of space. You could write down, say, an equation for the moon as a function of time. Now, if you write it down as a classical mechanics equation, in fact, those are written down, right? The equations of motion, the laws of motion, gravitation, etc. Just Newtonian mechanics can give you the function or the equation of the moon's position as a function of time. And what is more, we actually can write that down and get the answer like 1,000 years from now.